Hello guys, in this tutorial session we are gonna create a 5.5 gigahertz lambda by 2 dipole antenna on the Ansys Electronics software. So first of all we have to measure the length of the antenna. So to measure the length is lambda by 2 is equal to c by 2f. There is a c speed of light and there is a frequency that 5.5 gigahertz. Then we get the length of this antenna is 27.27 millimeter, but for some reason we take is 23 because in the Ansys there is some variations. We are not getting 5.5 gigahertz proper antenna on 27.27 result, so we take a 23 millimeter. So let's just move on to the end. So first of all we are going to the HFSS, then it will create this 3D views. So create this cylinder here and just choose the random size, then double click on the create cylinder tab here, and then we're gonna assign the position on the z-axis. We are gonna give it dl minus dl by 2, and it will ask you to define the variable. So in the unit we are selecting length and it is in mm. Make sure that it is in mm. Then we calculated that our length of this antenna is 23 millimeter, so here it is. Then radius dr, we are taking a 1 millimeter radius antenna. Then the height is our dl, only the length of this antenna. So yes, there it is. Then okay, if you guys face this problem, then if there is a hollow cylinder, then select and delete this again and then create the cylinder again, then it will fix this issue. So here we perform the same as we performed before, dr and dl our length, then apply. So now you can see there is the perfectly closed cylinder. So now we created the cylinder. Now we have to create a lump port. There is a subtract the 2 millimeters part on the middle of this cylinder. So we take another cylinder to subtract. So here it is the second cylinder. So here we are going to assign the dg minus dg by 2, which is the length of this subtraction part. So dg is also a length millimeter, so we take this length as a 2 millimeter. Okay, so the radius is dr, same as the main antenna, and the height is our dg. So okay, then apply. Okay, so here we have created. So firstly we just make this our main cylinder, change the color so we can identify it later and make it a little bit transparent. Okay, then this is our subtraction part, our the small subtracted part. So first we have to click on the main antenna, like we selected the main antenna, then press the hold the control key, then click on this cylinder 2. So here is the subtract option will be visible, so click on that, and there you can see that cylinder 1 blank part cylinder 1 and tool part cylinder 2. So keep it that way. The part you want to subtract, that will be on the right side and the main antenna will be on the left side. So you click on the OK, then it will subtract this. See here there is a 2 millimeter part subtracted from this our main antenna. So let's just now define this material of this antenna. So to define this, just right click on this antenna cylinder, say anything, so and then assign the material. So here we find type copper, so here system material copper, then press OK. So this antenna is become the copper material. So now here we are gonna create the lump port, the proper lump port. So we first subtract the part to make a place for the lump port. Now to make a lump port we have to make lump port between them. So here I am changing to YZ axis, so it will, you can see the grid. So now we are gonna take this plane, then just click anywhere, then create a random variables. So now here we have to make this the position of that. So here we are going to assign the variables here. So positions, keep it that way. Here make sure that axis will be x here. If you don't see the x-axis, then there will be a problem in your lump port. So here we have to define the y-axis size. So y-axis here is the radius of this antenna. So our 2 into dr, so radius, and there is a z-axis. That axis will be equal to dg, that our distracted part. So here if you click OK, then here that is our lump port is created. So now just make it as the, so here you can see that there is a lump port is created. So now if you click on that, there is a, don't have to change anything. So this is our antenna and there is our lump port. So now we have to assign this as it is a lump port. So what we have to do is the first go to unassigned, there's a rectangle, then right click on this option, then assign excitation, then there is a port, then click on the lump port, if you click on a lump port and the windows like that open, then you have to cancel this thing and just go to the this the HFSS menu. Then there is a solution type, so click on the solution type. Then there is a click on the options model, then check these things are selected, then click on OK. Then don't have to just follow again, right click, then assign excitations and port. Then here it is the lump port. Okay, then click on that. There is a lump port 1 here, don't have to change anything, just next. Then integration line, here we have to click on that, and integration line, create a new line. Then just click here or click here, anywhere, just click that. So that is defined, our lump port is defined. So now next, there is a impedance, make sure that there is a selected renormalize all modes 50, make sure that is a selected. If you select the do not normalize, then your lump port will not work properly, so make sure this setting, then click on the finish. So let us check that our lump port is created or not. So here you can see that there is the design, so our lump port is perfectly working, and this is in that direction. So yes, everything is look fine. So now it is the time to create this define the boundary, so where this antenna will work. So before defining the boundary, let us save this our project. So to define this a boundary, we are gonna first create the box somewhere. And okay, there is a problem here because we are in the 2D direction, 2D port. Now you can see that okay, there is a box created for any random size. So now we are gonna define this box size. So I am taking this size. Just make sure that your box is greater or more wider than the antenna, like your antenna should be in this box. So I will randomly choose this position 40 40 60, and then on the size we define the double size of this position. If the x-axis size is 40, then we x-axis position is 40, then we define 80 size. Sorry, here is the mistake, I have to minus for everything. Okay, so here 80, here is also 80, and here 120, then apply and okay. So here our box, like our boundary is created. So for that we are gonna give it another color, and that should be a very transparent. Okay, so it is our box, and this is our antenna, very little antenna. So now just go to the here. Oh, okay, sorry. Now click on the validate. So here boundaries are also excited, everything is fine. Now we have to just create the setup. So before that, if already thing created, but we are gonna make few changes. So here go to the assign material for this box again, then search for the air, then we change this to air. So let me just cross check it. So air system library. Okay, so air is selected. So over this box has a air instead of vacuum, here we created the air. So now define this box as our boundary. So here on this box, click and then right click on this, go to the assign boundaries, then boundaries, then go to the radiation, then there is a name radiation 1, then okay. So here our boundaries are here, that is our boundary radiation. So everything is done, let us save. Then what you guys have to do is to create a proper setup for this. So in here we go to the advanced setup, advanced. So it is our broadband, so low frequency. So for me, I am also gonna teach you about the if you vary the length of this antenna and the radius of this antenna, then how it will affect. So I will initially take this low frequency 4 and the highest frequency 7. Okay, then there is a maximum pass is 6. If you like 10, it doesn't matter if you change or not. Then go to this advanced property, save radiated field only, make sure that everything is perfect like as I did, then just click on the OK. Then this thing will appear. So here in the sweep type, you have to click on the discrete, and that is a start at the 4 gigahertz and end at the 7 gigahertz. Then either here the points, let us take as a 25 points. Okay, 25 points it will calculate. Then save radiated fields only. Okay, now everything is check. Now click on the OK. Then now validate. Here you can see everything is perfectly working. Then close. Then let us save. So now click on the analyze all to we can check this antenna is properly working or not. So I just click on this analyze all. So here our antenna is running, and here in the few minutes we will get the result. So guys, here the everything is done. This software has done all what we have done. Here we analyze all the signal, and here we are done with this. So now what we have to do is go to this results option in project manager, then right click on it. We have to first to check this antenna is properly working or not. To that, right click on it, then create a model solution data report, and from there click on this rectangular plot. So here there should be a, here the X default frequency, Y is a dB, S parameter S11, and it should be in decibel, and here domain should be in sweep, and solution we set up one sweep. So everything should be in that manner. Then create on a new report, and then just close it. So here you can see that, here you can see here on 5.5 our antenna is radiating. That means our antenna is properly working. Here you can see that there is a 5.4 to 5.5, nearly that our antenna is properly working. So that is our first, our S parameter. So now we have created this, then now we have to create a 2D two-dimensional plot of this this antenna. So to create that, so firstly we have to go to this radiation, and here click on the right, then insert far field, then create on this infinite sphere. So here we have to assign this phi and theta. So here we, for 2D we have to make this phi as a 0 to 90, and the step size should be 90. So this phi is normally basically the horizontal plane. Okay, so on the horizontal plane we want the total 0 to 90, and so for the theta we have to create the total 360. So here I am gonna take this minus 180 to 180, so it will be totally 360 degree rotation. Then click on the OK, then there is infinite sphere will be okay there. So here now so now go to this result, and from the result go to the create far field report, and from far field report radiation pattern. Okay, so from here, from last adaptive to we have to change to the sweep, there's geometry 2D, and from here hold the right control button, and then click on this gain phi and gain theta. Okay, and here select this decibel option, and there is the gain is selected here. So here you can see there is keep this that way, then create a new report. So here you can see that there is a that kind of a gain report we have got. So here you can see that gain plot, that blue and orange field is our radiating field in a 2D model. So now we are going to create a radiation field for the 3D model. So again right click on the radiation, insert a far field setup, infinite sphere. So here just keep this everything that way. Then here also our theta is also a 360 degree, and this that phi is also 360 degree. Then it is our 3D model. Then okay, that is our 3D. So again go to the results, right click on it, then create a far field report, and from the far field report go to the 3D polar plot. So here last adaptive to sweep, there is 2D to 3D geometry. So here there is a decibel, take it as a gain total only. Then okay, then just click on the create a new report. So yes, here we got our radiation gain plot in the 3D model. So that is our gain plot 2, which is a 3D. So yeah, that is the main thing we have to see. If that things are completely coming, then that is the finish of this our experiment. So yeah, and now we are gonna measure this for the when we change the length of this antenna, and then we change the radius of this antenna, then how it will affect the radiating field. But now we are gonna create the gain versus frequency plot. So click on the result, right click on that, create far field report, and from that rectangular plot. So here we are gonna set up the sweep, there is a geometry 3D, and from the primary sweep theta to frequency, here gain total, and there is a decibel. And from the families, here we gonna take the phi as a, actually let first take the phi as a 0 degree, and the theta as the 90 degree. So here it is the 90 degree, then create a new report. So here we can see that there is a our gain graph, gain versus frequency graph, the S parameter plot. So now we are gonna export this graphs here. So here go to the report 2D, then click on the export, and here I'm gonna say CVS to PNG format, and here I'm gonna click on the 4K. So you can choose anything image size you want. I'm choosing a 4K. So here S1 parameter plot and save. So it will save this graph to your PC. So here it is a 2D graph. So create. Now we are gonna change the length of this antenna. So let me just first disappear this boundary. So I just click on this I and cross button to disable this boundary. It is there, but we cannot see it there. So now we are gonna change the length of this antenna. So for that, go to the HFSS, then design properties, then our DL, the length of this antenna. So here from the 23, I am taking the 25, then apply and OK, then save and the simulation validate in OK, then analyze all. Then again we are gonna analyze this. So here our this is our S plot for the when we increase the length of this. So we increase this length to the 25. So that is the graph for the 25, the frequency. The 25 length. Then now we are gonna decrease the length. So we have initially 23. So now decrease the 2. Then we're gonna take it as a 21. So apply. Okay. Then now again in the simulation we're gonna analyze all. Then let's just create it for the smaller length. So here we can see that if we decrease this decrease the length of the antenna, then the radiating field is moving towards the 6 gigahertz, and if we increase the length, then it is moved to the 5. So we have to show the all these three like we can say that all these three characteristics in the one graph. So for that, there is we have to again go to the result, right click on it, then create a model simulation data report rectangular plot, and for here we have to check this. Here go to the families, and for the DL use all values, like for all DL values it will plot a new graph. So okay, then close it. So here we can see the different characteristic here. So let me just close it. So now here you can see that there is a what is the blue one. Here the blue one is for 25. If we increase the length, then it will decrease the frequency. Then if we increase the length, decrease the length, then it will increase the frequency. So it is the inversely that is proving that the length is inversely proportional to the frequency. So here you can see that lambda is the length, like L is equal to C by F. It is inversely proportional. So yeah, that is characteristic proved. So now we just get back to the design properties, and now we are gonna change into the radiation. Not a radiation, it is the radius. So let it just be a 23, our original thing. So for the radius change, so here we are gonna change it to the 1 point. Let's just make a very small radius change to 1.2 or maybe 3. Apply. Okay, then again simulation, then analyze all, and let us see what it comes. So this is for the 1.2 millimeter radius. So now we cannot see the much differences here. So let us just change it again to like 0.8 millimeter. Okay, so apply. Okay, so I have run this simulation for the different frequencies. So I am again creating the plot for them. So just don't have to do anything, just DL, just select this DL, the length is a 23, the ideal length, then the radius is for all the different radiuses, then add a new report, then close. So here you can see that if we increase the radius, then it will decreasing the frequency, and if it decrease the radius, then it will increasing the frequency. So here it is the plot for the radius change. So that's all in this lambda by 2 dipole antenna. All this plot you have to check for the antenna, and that is the antenna model. So yeah, that's all you have to do in this. Some things will be looks like it is complicated, but it is not. It is very simple. If you learn one time, then you will be get used to it. So thank you for watching, guys. I hope this video will be helpful to you.